So you're able to see me, I think, right?
Yeah.
Right.
We are able to see the slides as well as we are able to see your
Right.
video also.
Right. So when necessary, I may use notes as well. So please let me know if you're able to see this as well.
Yes, we are able to see this one. Yeah,
Right.
your writing pad, na? This one also we are
Right.
able to see.
Correct. Thank you.
So, shall we begin now, sir?
Yeah, we can begin.
Hello, all of you. Welcome to the third day session. Now we are having with us Professor Ramakrishna Sai Gorti, who is working as an associate professor at IIT Tirupati in the Department of Electrical Engineering. He is working there since 2017. Before that, he was associate professor at Indian Institute of Space Science and Technology.
Hello.
Vishwanath sir, you are not audible.
Yeah. Hello. I'm audible, right?
Yes, sir.
Yeah. Before Vishwanath sir comes, I just want to know, on the previous talks and the background of participants. So I hope all are familiar with neural networks. Am I correct?
Yes, sir. We have basic knowledge.
Yeah. So, and familiar with the back propagation in neural networks and gradient descent principles as well.
Yes, sir. Somewhat.
So, I'm sorry.
Yeah, please go ahead.
Our internet gone off actually. So, let me reintroduce Professor Ramakrishna Sai Gorti. I think this connection got lost some few minutes before. So, Professor Ramakrishna Sai Gorti, he is working as an associate professor at IIT Tirupati in the Department of Electrical Engineering since 2017. Prior, he was associate professor at Indian Institute of Space Science and Technology, Trivandrum. He was a postdoctoral fellow at INRIA during 2009 to 2011. and he did his PhD from IIT Madras. Before that, he did his masters in research from IIC Bangalore. Both were in computer vision. His teaching experience spans over signal processing, machine learning for image processing, deep learning for computer vision, and computer vision for both UG and PG students. He has to his credit 75 publications in reputed conferences and journals, which includes IEEE transactions on image processing, signal processing letters, pattern recognition letters, so on. He also published in top conferences like ACCV, WACV, ECCVW, ICCVW. Currently, his research interests includes visual tracking, deep learning applications in medical and satellite image processing, development of deep learning based 3D surface reconstruction methods. So now with this introduction, I am handing over the platform to Professor Ramakrishna Saigorthi Garu. I'm sorry that there was a disruption in our internet link. Sir, please go ahead. Are you able to hear? Sir, you have muted your mic, it seems. Yeah.
Yeah, sorry. Yeah. So thank you, sir, for the introduction. Today in this talk, I will be discussing on recurrent neural networks. I will be discussing from the basic principles of recurrent neural networks to some of the applications of them. I request all the participants to feel free to interrupt me at any point of time if they wish to have any clarification in terms of the concepts or in terms of their questions. I would like to acknowledge before I start Stanford team for using the some of the slides from their lecture series, and also Professor Mitesh Kapra from IIT Madras. Both lecture slides are have slightly different notation, but still they have some complementary and important aspects to be discussed. And now let us start our discussion. So see, before I start on recurrent neural networks, I would like to hear from the participants what you what you think are recurrent neural networks, and what applications do you think you would like to target with recurrent neural networks. So anyway, I will start discussing, and I will be discussing few aspects. Before I start that, I would like to hear from you on what background you had on recurrent neural networks. Probably you can tell, are you familiar with, as just I asked, with feed-forward neural networks and backpropagation? Yeah, very good. So I heard that you are beginners in this recurrent neural network. So on the yes, feed-forward neural network, like what applications do you think we can target? So let me be clear with a little bit of background you have, and then I can context or position the talk accordingly. So with feed-forward neural network, what kind of applications should we target? Can I listen some answers from someone? Okay, let me let us have a feed-forward neural network here. Okay, so hope you are able to see here. So here you have, see what does feed-forward neural network does. I just want to listen at least one answer on this before I discuss further. Yeah, I think even wrong answer is fine for me to start. Okay, very good. So somebody has said it can do classification and regression. Okay, very good. So can I get an answer for, say, example of classification task it can do? So you can give plenty of examples. I just want one example of classification task a feed-forward neural network can do. A time series data classification. See, time series data, what kind of classes you want to classify? I want a little easier example. See, time series data means there is a series of numbers coming. So you want to classify it as 0, 1, 2, 3, 4 there. Okay, like medical data processing. Okay, this is also a later example. So we need to specify what is the input that I am giving, okay, and what output I am expected to get in a specific task. That's what I am asking. Okay, action recognition. What are inputs and outputs? An easier example is to listen easier, like understand easier. Okay, video collection of frames input. Okay, what are outputs? Okay, let me coin specific problem then. Assume that I have some images of digits. Okay, this may be 6. Okay, this may be say some 0. Okay, and it may be some 5 and okay, I have several digits. Now what my task is, given any of these digits, so I can vectorize this digit. So assume that I have vectorized this digit. Okay, so this is vectorization of this digit. Say this digit is say 20 cross 20 pixels in unit. Okay, so and when I vectorize, the dimension of this will be 400 cross 1. Fine, do you agree or not? This I would like to give as input to a neural network, and I want to tell the output which digit it is. Then my question here is, how many number of output neurons should I have to perform this task, and how many number of inputs should I have for the neural network? Please answer me, because I will be discussing a little bit of theoretical aspects or mathematical aspects. Unless I am clear that you are like some background is set, okay, you will not be able to appreciate or understand what I discuss later. So how many number of, for this digit classification problem, how many number of input neurons has to be there, and how many number of output neurons has to be there for the classification task? Okay, 410, very good. Yeah, thank you. So we will have actually, so let us assume that there is 400 inputs. So like this, 400 input neurons, okay, and then 10 output neurons. Okay, 10 output neurons. So first output neuron will give high score or probability. When does it give? It gives high probability when I put input sample is 0. Okay, when 6 is given, so 6th output neuron may give high probability, right? So like that, these output neurons give probabilities corresponding to 0, okay, being higher, and probability 0 corresponding to 6 here, and so on. Every time these output neurons gives the probabilities corresponding to, okay, 0, 1, 2, 3, 4 up to 9, right? Hope you got the point what I'm trying to discuss. And this is a neural network. Okay, it will have how are the connections here? There may be some hidden layers and so on. Okay, so but let's assume that we have a very simple neural network. Okay, whether it works or not doesn't matter. We have a direct simple neural network. Okay, something like this. Okay, it has connections everywhere. Okay, to every other neurons and so on. Okay, similarly, this will also have connections. Okay, so this is a simple neural network we have. Fine. So do you hope things are clear up to here? And let us introduce the notation. So x1 and to x400. Okay, what are these x1 to x400 called in machine learning or classification tasks? Can I hear some answer? Similarly, I assume that outputs now y1 to y10. Assume that I have got the outputs. Okay, and I want to get the relation between inputs and outputs. Also, I want to denote these weights. Okay, let this xi be input. Okay, yj be the output. Okay, and the weight relating xi and yj. Okay, so weight relating xi and yj. Let this be wji. Okay, so this is matrix W consists of all elements wji. And now here are few questions I have. Okay, what does input xi is called? What is xi called? That is first question. Okay, second question for me is, what does say, how is that yi related to yj related to xi? Okay, and then what is the dimension of capital W? That encompasses all weight elements. So inputs, somebody has said their data samples. See, I want a better name for x1, x2 up to, yeah, input features. Very good. So input features is a very good name. So x1 to x400, we call them as input features. Okay. Even we can denote them as capital X, a vector X. Okay. Now let us come to the weight matrix. What is the dimension of weight matrix? Wji. Can some of you tell what is the dimension of weight matrix? 400 cross 10. Okay, so let's take it. So if I have the weight matrix, see, W is 400 cross 10, we are telling. Okay, so it is 400 cross. Say, let us assume that this is 400 cross 10. Okay, right. So now can you tell the relation between Y and W and X? I would like to hear from some of you, what is the relation between Y, W and X? Y equal to what? W into
X.
W into X. Okay, fine, good. So it is W into X. Is that alone? Or in neural networks, usually anything else will come in picture? Now, if the W dimension is 400 cross 10, okay, will this agree with this equation I have written? Y equal to W into X. Huh? So what is the dimension of W? Wji I have said. So the number of rows are 10. Okay, number of columns are 400. Okay, this is the dimension of W. And X is what? The whole vector. This itself is X. Okay, considering from x1, xi to x400. Okay, this whole thing is the vector X. Okay, and is there anything missing here? I would like to hear from you. X is 400 cross 1. Is there anything missing? I don't know whether you are sending some messages. Yeah, bias. Okay, fine. Very good. Bias is missing. Anything else? Okay, bias is fine. Anything else? There is one important thing that is missing. Okay, W transpose. Okay, not necessary. So if I take based on the W dimensions, I did not put transpose here because W I have taken it as 10 cross 400. Hidden neurons. Okay, that is okay, but I think that's not very important now. There is one very important thing. It say it will not be able to solve usually a complex problems unless we have that in neural networks. Activation function. Very good. So what is missing is activation function. Okay, so we should have here f of. Okay, so this activation function, I hope you know some examples of activation function. Okay, one simple activation function is sigmoid activation function, which looks okay something like this. Okay, so this is f of sigma is equal to 1 by r f of r. Let us write slightly differently. Okay, sigma itself is f. Sigma of x, okay, is equal to 1 by 1 plus e power minus x. Okay, this is the activation function. Okay, so this has this kind of sorry, this is minus 1 to 1 I have written, right? So just let me let us sketch this here. What is the range of this activation function? 1 by 1 plus e power minus x. 0 here. At minus infinity it is 0. Okay, and this is half at 0, and then at infinity it is 1. Okay, this is the activation function. One example of activation function. F of is equal to sigma here. Okay, so fine. So I hope this notation is what I am interested in. So if we neglect the activation function, then simply y equal to w into x. If whenever I have a neural network, okay, so simply what I have is, I have an input feature x, okay, I may have one layer, this is w1 if I say, okay, after this layer I may get some output y, okay, I may have another w, okay, sorry, slightly like this, okay, after this I may have actually z, okay, and this may be w2, okay, and then the outputs will come here, okay, so this z itself is the output. So relations, when you get y equal to, I can write f1 activation function f of w1 into x, okay, this is the relation between y and x. I have left the bias, okay, for ease of writing, okay, usually bias is also there, plus b, something is there, I just left it, okay, and z equal to w2 into y, okay, as you can see here, I can simply write like this, okay, and then I can relate the, see what is important for training a neural network. Now let's come to the next point. Okay, what is important for training the neural network? Yeah, I request, yeah, loss function, very good. So now let us bring the loss function into, so how should I have the loss function? Loss function is z is the output here, and desired output may be say d, or okay, targets t, okay, so in that case t is the output, so this is my loss function, right? How much the obtained outputs deviate from the targeted outputs, okay, that is the loss function I have. And now given this, what is the problem of learning neural network? Okay, what do we say, say what should we learn in neural networks? I request some answer, quick answer. So what is that we need to learn in neural networks? Or what are to be decided, right? Very good. So we need to learn these weights. So for learning the weights, what the principle we use is what? What is the principle we use for learning these weights? Training parameters are weights, very good. And weights and biases, okay. And what is the learning procedure that we apply?
Back propagation, sir.
Yeah, very good. So we apply back propagation. So, and gradient descent is the principle mainly that we use. And now, see, assume that if I want to find dou j, okay, by dou w1, okay, w2, okay, I need to do differentiation. How do I write dou j by dou w2? Because these all are directly applicable in recurrent neural networks. Dou j by dou z I will write, and then dou z by dou w2. Like this I will write. Fine. And let us target only the second one. So dou j by, okay, dou z. Let us anyway write both. Anyway, we need to write there. So what is dou j by dou z in vector form? Can one of you tell what is dou j by dou z and what is dou z by dou w2 here? Okay, we need to tell both, but also tell dou j by dou y. Also what? Okay, I need these three answers. Okay, so can some of you quickly tell, don't bother about f dash, assume that for simplicity, assume that f is equal to linear. Okay, that means f is just a straight line. So z equal to simplicity w2 into y. Okay, so that actually our at least writing and other things will be simpler. Okay, so later you can bother about f is as well. Whenever f is there, f dash comes into picture. Okay, so in back propagation. So that I think you might have listened earlier. So first dou j by dou z. What is the answer? Can one of you quickly tell? Okay, z minus t, very good. And what is dou j by, dou z by dou y in vector form? Dou z by dou y. So this is z minus t, good. And then what is dou j by, dou z by dou y? Any answer? Okay, I will write here. Okay, right. So dou z by dou y is equal to what? W transpose. Okay, you can check it. Okay, when z equal to w into y, okay, dou z by dou y is equal to, okay, please note this. Okay, dou z by dou y is equal to W transpose. Okay, so W transpose means here W2 transpose, because we have taken here W2 as different weight matrix as W1. Okay, when this is very important relation in matrix, you can verify this. Okay, whenever there is a z equal to w into y, dou z by dou y is equal to W transpose. Okay, this is, I will be keep using this relation. Okay, and even for understanding the when the recurrent neural networks converges, when they doesn't converge, for all these things this is important. Okay, whenever you have a function y equal to w into x, okay, so what I'm saying is dou y by dou x is equal to W transpose. Okay, so this you should be familiar, right, across the discussion of this talk. And dou z by dou w2 is how much? Is y transpose. Okay, so this also you will be using at some points of time. Okay, so for time being, it's not exactly y transpose, so it will be slightly different than y transpose for into something, but let us leave this. So this may not be very important for time being. Okay, so let us like this dimension of w2 is how much? Say if dimension of this y is h, okay, and this is d and this is o, then this is o and this is h, right? And hence the dimension of this is o cross h. Okay, and this dou z by dou w2 in fact is a it's not a matrix. Okay, it is in fact it should be a tensor. Okay, so let's now don't bother about this more for this time being. So it will come in terms of some delta functions and so on. Okay, let us not bother about this at this moment. Okay, but this is important as a rule we use frequently. Okay, so now let us start our discussion on the recurrent neural networks, given this little bit of background on feed-forward neural network. Okay, so see, now I would like to hear from you again. So what background, like you said, you are beginners to this recurrent neural networks, but what these recurrent neural networks are different, or from feed-forward neural network, are different applications that they target is based on the architecture of these neural networks. See, whenever we have a sequence of numbers coming in and we would like to predict the next number, or whenever a sequence of say letters coming in, and in a word I want to predict the next letter to fill the word, or when there are words coming in to fill the sentence, I want to predict, or I want to learn what should be the next word has to come. Okay, that all can be done conveniently through these recurrent neural networks. So what kind of these examples, as you are examples for sequence to sequence models. That means, see, for example, if I am telling a sentence, okay, so he is running. Okay, so he is, if I write based on the context, okay, the neural network itself has to tell that it is running. Okay, so if I have an image and I would like to describe that image with an example, okay, that with a caption. Okay, so in that case, we give a image or image features to the neural network, and we would like to tell what the caption of it. So we have given an image, fine, but we want to learn a sequence from the neural network. This is the example where we want to learn a sequence. Say another example, assume that I have a question and I would like to get the neural network give the answer. Okay, so what is he doing is my question, and neural network has to tell he is running. Okay, so how does it tell? It learns somehow from a sequence to sequence, say based on the previous discussion that has happened, it may be able to tell he is running. Okay, so something like that. So are you in some cases, say if I give a small few sentences, 2-3 sentences, and if I wish a neural network to summarize it, okay, in terms of a single sentence or a a couple of words, okay, how does it summarizes? It summarizes again learning a sequence to sequence learning. Similarly, assume that I have a time series data. Once I have time series data, from that I want to tell what will be the next number that comes. I have stock market data and I would like to predict what will happen in the next instant. Okay, so the cost, etc. Okay, in that case, what we are trying to say, we have a sequence in hand. That means this sequence has a meaning, okay, and a connectedness. From that, we would like to tell what the next sequence will be or the next numbers will be. Okay, that can be effectively done through recurrent neural networks. So if you see the major difference between feed-forward neural networks and the recurrent neural networks, okay, the main difference is in terms of what? The main difference is in terms of the temporal learning that these recurrent neural networks has, which is not being there in the conventional feed-forward neural network. So for example, if you, so far you have seen the classification task, okay, and regression task. In the classification and regression, you don't need to give a sequence of images and tell that this image to this image, this has relation, this much relation. That means all the images I give are same class or different class. That information we are not using it there. We are just giving that instant and taking a answer for that instant. That is what is being done in conventional neural networks. Whereas, okay, in recurrent neural networks, what we do is to learn a sequence to sequence or an image to sequence and so on. So there is a temporal learning that is happening. Okay, that is one of the main aspects of this recurrent neural network. Now let us give some examples. See, these recurrent neural networks, okay, may also have a similar structure as that of feed-forward neural network, okay, in to some extent, but they have a additional temporal connection. Okay, so that is referred to as recurrent connection. Temporal connection means, okay, from time t0 to t1, there should be some information that has to be transferred. Similarly, from time t1 to t2, there has to be another additional information that has to be transferred, and so on. Okay, so now you can see based on this discussion, if you have a single input layer and a hidden layer and an output layer, there are several possibilities that in which I can connect them. See, in some case, I may have only single input and multiple outputs. I may expect at every instant you see that there are temporal connections here. Okay, so and then the number of outputs and inputs may vary depending upon the application. Okay, so let's say assume that we have a problem of image captioning. I have one image. From that, I would like to tell what is the what is going on. Say for example, there are some students and a lecturer there. We can say that from the image, okay, we extract some features and we have a connection across these features to temporarily give the word that a class is going, okay, and a lecture is going and something like that. So it has to describe not in just one word or in a letter, but it has to tell in a couple of letters or in a couple of sentences. Okay, so that is one example of one-to-many kind of recurrent neural network. Similarly, can you tell some example for many-to-one recurrent neural network? So can I hear from participants on the example of many-to-one recurrent neural network? The example for this is, say for example, if I have several video frames in a video and I would like to tell what kind of video is it. Okay, I may have a short clip. Okay, 10 frames I have. So in that 10 frames, I just want to tell, okay, this video is about, say, marketing. Video is about, say, education. Video is about, say, medical diagnosis or something like this. So if I give some classifications or some number of classes, and I would like to put based on these video frames to one category. Okay, that is an example of many to one. Okay, also here sentiment classification. See, Twitter, for example, somebody may tell some sentence and say we want to tell whether this whatever he has written there corresponds to positive like comment or negative comment. Okay, or neutral comment. Okay, this is one example for many to one kind of recurrent neural network. Similarly, there can you think of some examples for many to many kind of classifications? One example is, say, machine translation. So I may have in one language, I would like to hear in another language, English to Telugu, for example, or say Hindi to English, and so on. Or machine transliteration. I just want to tell exactly same whatever is there in this, but in another language. Okay, something like this. Okay, so like we chat in WhatsApp kind of thing. Okay, so or we would also for any other example for this is conversation machines. Okay, so if I want to get a question, if I give a question here, I would like to hear an answer here from the recurrent neural network. Okay, so please note that there are temporal connections or connection across each of the hidden neuron in this. There is no such connections. See, this is, if you see a feed-forward neural network, this alone is a feed-forward neural network. Okay, and you can consider this as, in fact, if you see here, this is a feed-forward neural network, and this is a feed-forward neural network, and this is an independent feed-forward neural network. So in kind of classification, we don't connect them temporarily. Here in recurrent neural networks, there is a feedback connection, we can say, because from time t0 to t1, that information is passing. Okay, from the hidden neurons. There is a temporal connection across different networks that are operating at different time instances. This network or this feed-forward neural network operates at time t0, and this feed-forward neural network may operate at time t1, and so on. Okay, so something like that. So now let us see these examples are conversation machine and so on. Okay, and can you tell one example for this? Many to many. Here I am giving a assume that there is, I am giving a set of frames, video frames, and I would like to classify each frame into one like classification task. Say I want to tell what this each video frame has a person, has a bike, or has a any aeroplane, and so on. If I put some classes and I would like to classify each of these frames, then I can do it. Or action, for example, each frame, is it a laughing expression or a like anger, and so on. So I can pose problem in different ways. Now let us see a structure of a recurrent neural network. Okay, so as I said, we have an input and output and a hidden neuron. Hidden neurons just similar to feed-forward neural network. Okay, this structure, if you see, this is similar to feed-forward, and this is the one making this recurrent neural network different from feed-forward neural network. What is this connection doing? See, each of these are, this is a feature vector, and this connection is nothing but weight matrix. Okay, that is giving hidden neurons here. Okay, I will expand this in the subsequent discussions. And this is again a connection, means another weight matrix that is giving output y. Okay, and this connection is again a weight matrix that is connecting temporal hidden neurons at a t-1 to t. Okay, so this FW is a function that connects through a set of weights from ht-1 hidden neurons at t-1 to hidden neurons at t, as well as the input at t to hidden neurons at t. Okay, so input to current hidden neurons and hidden neurons at t-1 to hidden neurons at t. I hope this discussion is clear. And this connection makes the recurrent neural network different, and also training of recurrent neural networks challenging. Why? Because see, you can see that, see, each of ht is dependent upon ht-1 with same weight vector, and ht-1 is also dependent upon ht-2 with the same weight vector. See, we cannot have different weight vectors for connecting the temporally across different different times, because we do not know a priori how much is the length of the sequence. Okay, how much is the length of sequence we want to generate, how much is the length of sequence we give for question, how much is the length of sequence we need to get answer. Okay, so they keep changing. So you cannot have a completely different architectures and learn every time different new weight matrices. Also, the job they do across the temporal direction is roughly the same, trying to relate the previous state of hidden neurons to current state of hidden neurons. So, and then previous state to current state, previous state to current state, and thus the work they are doing, the like purpose they are solving is exactly same, and hence it is justifiable and required to have a same weight matrix that goes across time and that gets updated also across time. Okay, so that thus what happens, see the weight matrix that I have this making this connection. Okay, so if I now explicitly write in terms of weight matrices, this is how it looks like. Okay, so if you can see, HT is the one hidden neurons, HT are the hidden neurons, and is a function of HT minus 1 with WHH. This is the weight matrix connecting HT minus 1 state to HT state. Similarly, this weight matrix connects, okay, input features at time t to hidden states at time t. Okay, and these two weight matrices need to be updated for like at instant time t. Okay, similarly, there is another weight matrix that connects these hidden neurons to output, that is YT, through WHY, okay, into HT. And this Y, from here you get the output, and to train the recurrent neural network, what we do, this output we compare with the desired output, okay, whether we are getting the same or not, and then use that for back propagation. Okay, so hope the things I have discussed so far are clear. Okay, if you have any questions, you can ask me now. I will give a little pause. Okay, just for 1 second. Okay, this is the like feed forward recurrent neural network with different states shown here. As you can see, at each state there may be different input that may be feeding. Okay, and output also may be different. I also will decide from which hidden state I would like to take output. Okay, I can take from here, say I can start taking output from here, I can start taking from output from here, and so on. It is the design parameters. Okay, and then these weight matrices are again to be learned as a process of recurrent neural network. And how do we learn? Through the loss function that comes at the output of each of these output like layers of the state T0, T1, and so on. Yeah, I request for any discussion at this point of time, and if we have no questions, we will move on.
Sir, I have a question.
Yeah, please go ahead.
Sir, I am not aware of the literature of this RNN.
Right.
But if you see this residual network, for this residual networks,
residual network is different. Right. Yeah.
Yeah. Whether this RNN, these recurrent connections are the motivation for residual networks.
Okay. Yeah, I think I'm see, residual network means that is say comes under skip connection, right? So they are with say resonates and so on.
Sir, I'm asking in terms of gradient flow.
Okay, gradient flow we will connect to this recurrent say residual networks at little later point of time. So these also share some of the ideas from residual networks or residual like resonates. So for better training of them, that we will discuss it say when we discuss about LSTM, long short-term memory.
Okay.
At this point of time, these are you can consider that these are different. So both are completely different. When we bring in that technique, we can see that there is some commonality that is used for training these better.
Thank you.
Yeah. So any other question? Right. So I am hoping that the discussion so far is clear. So now let us move on to some of the mathematical aspects. Okay. So since we discussed about how exactly the loss function happen at each of the recurrent time steps of this recurrent neural network. Let us take at one time step and try to see what like how do we get we update the weight matrices. Okay, so let us now start the discussion on this, and then let us go back and see the some of the slides to understand them better. Okay, so this is what we have discussed in the morning. So like just before, so you can see that this is the discussion that we had regarding the regarding the feed forward neural network, right? So you're able to see the mouse, I hope, right? So I'm moving here. Fine. You're able to see the like hand where the
Yes, sir.
yeah, right. No, fine. So this is exactly the discussion that we had in the morning. So dose A by dou X referred to as delta X is equal to, so dose dou Y by dou X. See here, Y itself is the output. Assume for simplicity we take only one layer. Also for simplicity we do not bother about this sigmoid activation. Okay, because that later anyway F dash will add because of this sigmoid activation. Okay, whenever that is important to discuss, we will bring in. Okay, especially when we want to discuss about any other aspects like diminishing gradients and so on. Okay, so otherwise let us consider this Y equal to WX, simple connection. Okay, linear neurons here, and then dose A by dou X. Okay, when we want to find, how do you find this? Like this. Okay, so dou Y by dou X. Dou Y by dou X, as I said in the discussion, it is W transpose, right? And dose A by dou Y is Y minus Y truth or Y minus T, that is delta Y. Okay, so this is the notation we have. Similarly, dose A by dou W, if you want to find, okay, how do you find? Dose A by dou Y into dou Y by dou W. Dou Y by dou W, as I said, so it can be written now in this way, you can write comfortably, delta Y into X transpose. Okay, here it comes as the final expression of delta T. Okay, because this is a scalar, it is easy to write the derivative with the matrix W. Okay, so as I also discussed, dose A by dou Y, sorry, dou Y by dou W. When we differentiate dou Y by dou W, we can write in this case it is X transpose. Okay, in this case we can write it as X transpose this side. Okay, fine. Given these basic things, let us move on to the discussion of recurrent neural network. Okay, so the compact representation of recurrent neural network is like this. Input features are here. This is the weight matrix. As I said, this connection means it is a weight matrix connecting the input features to hidden state, and then this is the weight matrix connecting hidden state to the output. So everywhere we are denoting WYH. Okay, connecting H to Y. WHX. Okay, so please note the notation. And WHH, connecting H to H. HT minus 1 to HT. And this in expanded form we will write like this. Both are equivalent. Okay, please note that there is no difference between these two in writing. Okay, so now let us move on. So we can start from H0 state and then keep going. Okay, like this, H1 state, H2 state, okay, and so on up to HT minus 1 state we are and HT state we are. Okay, so now let us write the expressions, mathematical expressions. So HT, now if I want to write, see mathematically if you want to write HT, how do I write? Same discussion that we had. HT depends upon XT and HT minus 1. Two things. So XT and HT minus 1. WHX into XT, WHH into HT minus 1. Okay. Similarly, YT depends only on HT. So it is WYH into HT plus biases. Okay. And the like at any instant I may have a output and a true output. Okay, desired output. So this is the error. I have error for my loss function to back propagate. Okay, so I can consider different kind of cost functions just like in feed forward neural network. I can have a regression kind of framework, or I can have a classification kind of framework. Okay, just in the at the output layer, just as in feed forward neural network. Okay, so only thing that differs between this and feed forward neural network is this recurrent connection. because of this recurrent connection, updating this WHH is not very trivial. Okay, because if you want to update WHH, you should not only look at, okay, at this instant. Okay, WX, say if you want to update WHY, it is fine. You can look at only at this instant. WHX, it is good enough to look at only at this instant. But WHH, you can't just look at it this instant and update. You should look at all H3, H2, H1 and so on up to H0. Okay, all these things you have to bring in. So the back propagation because of update here will also influence update here, okay, and so on. Okay, so you should have WHH when you update. There is a recurrent expression that comes. Okay, that we should keep in mind, right? So now let us see how do we learn it. Say assume that I want to predict here, say deep learning. Okay, so first I want to start with deep. Okay, so D I have given here. Output of the network has to be E, right? See, you know how to convert a word to vector embedding, right? So it's in similar way for each of the letters also we can consider one one numerical tag. Okay, so if you have only some set of letters to be predicted, what we can say is if as many letters are to be predicted and stop. Okay, stop character to know where to stop. Okay, so these many classes we have with us in the when we pose it as a classification task, right? So if you want to predict deep here, what should have D, E, P and stop. These are the different letters that we have with us. Only 4 different letters. Okay, even it doesn't depend upon the length of the word we want to, or the number of letters in a word that we want to predict. It only depends upon the different letters that I have in a in whatever I want to predict. So here only 3 different letters and a stop character. So let D be 1 and E be say like 100 for D. Okay, 0100. This is a 1 hot encoding. Just exactly like we do in terms of classification task. 10 classes make 1 hot encoding 1000, 0100 and so on. Right? Hope this is clear. Now I am giving D here as input. And now if we give D as input, I am expecting the output to be, so 0, say what I am expecting, E has to come. So 10100, this is the output I am expecting. But what I got, okay, in the network, because the weights are randomly set, I got the output 0.1, 0.08, 0.8 and 0.02. So you can see that the output is giving more probability for P rather than E. So this is not correct. And hence this is the true label and this is the obtained label and there is an error. And this error has to be back propagated. So when you consider cross entropy loss, you can see that the loss function L1 is equal to minus log of, okay, true class probability, okay, plus 0. It will come like that because other are 0. True class 1 into true class probability only comes as the loss function. Okay, minus ln of YTC. Okay, and if you consider mean square error, so 1.1 minus 0 whole square plus 0.01 minus 1 whole square and so on. Okay, that is mean square error. So you should know how to construct the loss. Okay, when you design neural network, these are very important elements. Probably you might have had by now. Okay, once you get the construct the loss, see now P I got. Okay, so what this recurrent neural network we have the provision is this, since I want to predict the word, all letters of a word, I can give this letter also as input here. Okay, so and this as input as the second to the second temporal location, say at time t1, and I want to predict now D, E, E, P, right? It has to come. So I will give, but output I got is only P. I have given this output and it has to give E to me. It has luckily has given E. So there is no error here. Okay. So here again E I have given, but E if it predicted, no error. Okay. But what it has to predict? So D, E, P it has to predict. So there is an error here. Okay, again. It predicted, but it need to predict P, there is an error. Okay, similarly here, so it has to stop. Okay, the output is here stop character. Okay, that is desired output. Okay, so and there is error here at this output layer, at this output layer, at this output layer, at this output layer. I consider the error set 4 output has to be L1 to L4 and sum the whole thing to get the total error. And this I want to use it for adjusting all these WHYs, all these WHH, WHX and biases. Hope this is clear. Up to this, the discussion is clear. Okay, now let's move on. So I want to first find dou LT by dou WYH. Okay, so dou LT by dou WYH if I want to find. Okay, so how do I find? See, that means I want to first update what? I want to update first these weights. Okay, see, as you can see, these weights depend upon what? So only they are related through YT and HT. And YT is there in L. So if I want to adjust these weights, what will happen? Dou A by dou L here, dou L by dou YT has to be written, okay, into dou Y by dou WHY. Okay, there are two steps to go in the update of dou HY in back propagation. Okay, so that's what we have written here. Okay, dou L by dou WYH is equal to dou L by dou YT into dou YT into WYH. Okay, so dou L by dou YT, if you see, it is delta YT. Okay, sorry, I have written this reverse. Okay, you can take this as first and this as next. Okay, delta YT into H transpose. Okay, so you can see the dimensions here. H transpose is 1 cross D, 1 cross N, number of hidden neurons be N, and Y is number of output classes, that let it be C. So it is C cross N. That is agreeing with YH. Y is C cross N. Okay, so this is one easy check for you whether what we are doing in update etc. is correct or not. Okay, the dimensions are easy checks. Okay, so as now let's move on. So updating WYH is very easy. Similarly, WHX also you can update with a little bit of back propagation. So dou LT by dou YT, dou YT by dou HT, dou HT by dou HX. Okay, just one more step of back propagation because you have to cross HT now. Okay, you have to cross HT and come to dou WHX. Okay, so let's go. This we can write each of them. So this dou HT by dou WHX, if we see, so you can see the expression here. Okay, where is this? Dou HT by dou YT by dou HT. Is how much? It is WYH transpose. Okay, so let dou HT by dou WHX is X transpose. So I think these are in reverse order again. Okay, so you can see that dou LT by dou YT is delta YT. Okay, and dou YT by dou HT is W transpose and XT. Okay, so please see that actually, see few of them dou HT by dou WHX. This is vector to matrix derivative. So whenever vector to matrix derivative, okay, there will be delta functions as I said before. They will change the order while writing. So they will not stick to the exact order of writing. So they will write X transpose in other side and so on. Okay, because of that, this has come in this way. Okay, so you can see X transpose. Okay, so you can see again the dimensions, they agree. Okay, and this is how we write the update here. Okay, so if you know the basic updates, how to write for dou LT by dou YT, that is delta YT. Okay, dou YT by dou HT, that is WYH transpose, and dou HT by dou WHX, that is X transpose. Okay, so if you know these things, X transpose bringing this in this side. Okay, that means this whole thing, okay, into this side. So if you know these basic steps, you will be able to write this. Okay, with a little bit of care and dimensions. Okay, so now for understanding this back propagation procedures, there is the formal way of learning or understanding is through computational graphs. So if you are interested more to know exactly about how exactly to write these things, I would recommend you to understand little bit or learn little bit about computational graphs. Okay, so for back propagation, here I am just providing a basic idea on which terms will come and how they come. Okay, so now let us focus on how do we update WHH. Let WHH, as we said, is a connecting weight from T minus 1, HT minus 1 to HT minus HT and HT to HT plus 1 and so on. So as I said, updating this is not very straightforward, and you can see it now. Dou LT by dou WHH, if we see dou LT by dou YT, dou YT by dou HT and dou HT by dou WHH. Okay, this is through back propagation chain rule. Now let us concentrate on this, because the other things we have seen how to write them. So dou HT by dou WHH when we want to write. See, now let us see here. So let us have a little bit of discussion on this. So assume that I want to write dou HT by dou WHH. Where is it? Yeah, dou HT by dou WHH. So now what do you think I should consider for writing it? Okay, so let us do it here. Just this alone, let us do it here. Remaining things, as I said, you can easily understand from the discussion that we had. So now assume that there is a recurrent neural network. Okay, and this is a anyway X, and this is anyway, let this be. Okay, I will erase this for without connecting this. Okay, this is Y. Okay, and this is Y1. Okay, assume that this is X1 and this is H1. Okay, and you started from H0, and here you have WHH. Okay, and here WHH again, same weight matrix will be there, but it will connect to H2 now, and here input is X2. Okay, and here, okay, and what you get is Y2, here Y1. Okay, and here after getting Y2, okay, you will use this to get L2, and this you will use to get L1. Okay, L1 means, you know, right, half of Y2 minus, okay, target 2 whole square. Okay, similarly for others. Similarly, assume that you have again WHH here, okay, and then connecting to H3, okay, and so on. Okay, I will not go through full derivation, but I would like to give idea very clearly, okay, so that you can appreciate what is the complexity involved in learning recurrent neural networks, L3, and so on. Okay, let us take like this. And finally, you got to H4. Okay, let us take up to H4. Okay, X4. L4. Okay, so like this, it keep going. So now what we want to do is, so we have written HT minus 1, the expression HT is equal to as function of HT minus 1 comma XT. Okay, and this explicitly is equal to WHH HT minus 1 plus WHX into XT. Okay, and this is equal to HT. Now we had a term here to find dou HT by dou WHH. This is what we need to find. So now I would like to hear from you an idea of how do we do it. See, if you want to do it, if we assume that this is independent of independent of WHH, okay, then you can simply find it. Dou H by dou, like dou HT by, if you, this is independent of WHH. Okay, if this is independent of WHH, then dou HT by dou HT minus 1, sorry, dou WHH dou WHH is equal to how much? Can one of you tell quickly? If this is independent, then I can write it as, in some sense, HT minus 1, even though it is not purely the same. As I said, there will be some delta functions to take care of the dimensions. For simply, we can write it as, okay, WH is equal to some HT minus 1 and something. Okay, so we can at least write this easily. Okay, but however, is HT minus 1 independent of delta? Is it independent of WHH? Is this independent of WHH? Okay, or is this independent of WHH when I write derivative at H4? Yes or no? It is not independent, because H3 also, if you expand it, okay, what will come? HT minus 1 is equal to again WHH, okay, into HT minus 2 plus, okay, WHX into X, okay, it's XT minus 1. Okay, so you can see that it is not independent of, okay, this is not independent of, this is not independent of WHH. Similarly, this is also not independent of WHH. That's where it brings in the complexity. And hence what you need to do is, see, when it is not independent, what do we do? Let us write like partial derivatives. We assume once this is independent and we write a derivative with respect to this, and we write derivative with respect to this. Other time we assume that this is independent and we write derivative with respect to this. Okay, so explicit derivatives and implicit derivatives we will write. So I assume that now I will write only explicit derivative, that is HT, that is explicitly if WH is present, that only I will count, otherwise I don't count. Okay, that means this is independent, I will count. Okay, that is explicit derivative. Explicit derivative means this is considered independent in explicit derivative. Okay, that is when I write with plus sign. Okay, but this is not the whole thing. What I need to also write? I need to write implicit derivatives. See, now I can assume WHH is independent. Okay, and I can write, see, I can't completely assume, say what I will write is, see, I will write dou HT by dou HT minus 1. Okay, I will first write it as derivative of HT minus 1. I don't bother WHH. I assume that it is constant. Okay, this is into, okay, but there is an internal derivative because HT minus 1 also is dependent upon HT minus 2. So HT minus 1 by dou HT minus 2. Okay, sorry. Right. So dou HT minus 2. See, you can see here into, so sorry, 1 minute. Okay, so dou HT by dou HT minus 1. Okay, that is the directly here I have written, but dou HT minus 1 is also function of dou WHH. So I will write it here. Okay, so I have written it in 2 steps now. This is explicit derivative and this is implicit derivative. That means this HT minus 1 also has function of WHH. That I have accounted here. Now what I will do is, okay, so I will try to expand this term further, because is this term directly can I write? This is exactly like, say for example, HT. So this I can substitute from here. Okay, if I assume, yes, right. So this term now, if you see, okay, this term is exactly like what you have this term. Okay, so I can write this term fine. Okay, but this term I can't write exactly like directly like, okay, this also has 2 variables, okay, that are dependent upon WHH. Which are they? HT minus 1 has 1 variable as this and second variable as this. Both have the term WHH in it. So again, this has to be expanded. So how do I expand it? So if I want to expand this, so I will again write, okay, so dou HT minus 1 by dou WHH. Again, I should write it as again explicit derivative by dou WHH. Okay, plus again implicit derivative dou WHT minus 1 by dou HT minus 2 into dou HT minus 2 by dou WHH. Okay, here it is explicitly if WHH is present, that only accounted. Here HT minus 2 is also function of WHH, that is accounted. Again, now what should I do? This is again a problem. So I can't just leave like this. So this again I have to write. Okay, so like this I keep expanding. finally I will put all of them in one expression for writing dou HT by dou WHH. Okay, so I have done all that, and you can see here after doing all this. Okay, so I have written those explicit and implicit derivatives. See, I have expanded this again. Okay, so here and I put everything in one expression. You can see here, first this comes with explicit, implicit. Okay, and second thing also is expanded, t minus 1 instant, explicit and implicit, t minus 2 instant, explicit and implicit, t minus 3 explicit and implicit, and so on. Okay, so now if I write all these things in a simplified form, how can I write this? See, please note here. So dou HT by dou HT minus 1, when I multiply with this, dou HT minus 1 by dou HT minus 2. These two together, how can I write? Dou HT by dou HT minus 1 and dou HT by dou HT minus 1 by dou HT minus 2. I can write this as dou HT by dou HT minus 2 directly, right? Similarly, at this stage, okay, all that I can write it as dou HT minus 1 by dou HT minus 3. Dou HT by dou HT minus 3 directly into what? Into the explicit derivative will come. So this can be simplified. I request you to work on at your homes to get the clear picture of it, because unless you work on once on this, it will not be clear. Here what I'm doing is to give a base idea of how it is done, because you should understand backpropagation to understand the recurrent neural networks better. Okay, so now you can say that actually this weight update is equal to, right, dou, this is explicit derivative at that instant, tk minus 1 instant, into its relation with respect to ht by ht minus k. Okay, and over all times till time capital T, from starting 0, okay, small t, time small t till 0. Okay, so 0th instant or t minus, say t minus capital T instant to tth instant. We consider all of them to write the derivative for the, okay, with respect to update the weights. See, why are we writing all these derivatives? Can I get a quick answer? Why we are concentrated on WHH, derivative of WHH, derivative of WXY, sorry, WHX, WHY, okay, or YH and WHH. Why I am discussing on these derivatives alone mainly? Do you have any answer? Because these are the weights to be updated. Okay, at t plus 1 instant is equal to WHH at tth instant minus eta times, okay, dose A by dou WHH. Okay, so if I know this delta, say for example, this delta WHH, which is equal to dose A by dou WHH, okay, I use only that for updating my, okay, for updating my weights through gradient descent. Okay, backpropagation. So now, so this is how the recurrent neural networks backpropagation happens. I would like to give again another pass here for any questions. So then I will move on. If you have no questions, I will keep going. So I request you to give a a little bit of time for any questions so far that we have discussed on the topic like backpropagation of recurrent neural networks that we have discussed so far. No questions? Sir, up to what time can I take?
Sir, actually the session is up to 11 o'clock.
Right, right.
So still there are 15 minutes are there.
Okay, fine, sure. So yeah, maximum up to 11:05 or 11:10 I can take.
Yes, yes, please.
Yeah. So maximum up to 11:10 I will try to. Yeah. Okay. So let's move on now. So you can see here the the recurrent neural network. Now this is the from Professor Mitesh slides. As you can see, they have slightly different notation. U for connecting WHX and WYH is V and WHH is W. Okay, so same discussion that we had is being done by him. So we will skip all this. Okay, so this is the like pictorial depiction of what we have seen. Okay, at different instances of learning. Okay, so and let's move on. This is the total error when we write. Okay, is L1 error in L1 plus L1 L2 plus L3. So same thing he has depicted pictorially, saying that this W is not only connected to state 4 but is connected to all the states. So in back propagation also it involves all the states. Okay, so whatever we have derived, exactly the same thing here. Okay, so you can see that back propagation is written in this way, right? So now let us move on to understanding. So this is referred to as back propagation through time, and this is also referred to as recurrent neural network, simple recurrent neural network, or recurrent cell, like building block of recurrent neural network. Okay, so now let us see what is the issue with this kind of architecture. Okay, and also understand what say like with this architecture what we can do. We will see first, then we will see what are the limitations of this architecture, and then go to short long-term memory. Okay, LSTM. So with this, what we can do, we can learn a sequence to sequence. Okay, so you can predict a word, is all letters of a word. You can predict, say, hello here in this example. Okay, and you can see that the recurrent neural network, when it is trained, it captures good features at different hidden neurons. Okay, so if you see this hidden neuron across all cells, then it is showing roughly the like some of the brackets or semicolon and so on. Okay, some syntax based aspects. So some other cell may be showing end of the line. Okay, some other cell may be showing some pieces of if conditions and so on. Okay, so you can also demonstrate through a little bit of understanding of each of the neurons job, what aspects they are learning. Okay, so now let us see an application of it to image caption generation. So if you have an image and we would like to generate a caption of it, okay, a woman at sea, for example, here. So what we should do is, see, we have the information of the whole image. We should effectively use it. So what is the best method for extracting the features in an image is the convolution neural network. Okay, so if you like feed forward neural network, the convolution neural network also has a feed forward architecture. However, it has the convolution operation at each of the layers to extract better and better features. Okay, so those who are familiar with say correlation can relate this to correlation with kernels or the filters at that layer. Okay, or convolution operation in signal processing or signal systems, they can easily relate it to convolution operation for extracting edges or corner points or any image features. Okay, so through that operation, the convolution neural network finally generates good features for this image. Once there are good features here, what we do, we would like to give these features as input. But at the same time, this is a image caption generation process. So each of the say for example, a woman standing at sea, for example, A first has to be start as I need to tell to the network. Okay, it will start. Assume that it has generated somehow A. Then the next words in a sentence are dependent upon the first word. So I should feed this as well. So there should be two inputs. So I can feed this itself as one input and this as another input. Okay, so you can see here, when previously we had only the current state depends upon only previous state. Now what we are doing, image features are also given. Okay, so these image features can also be given to each of the hidden states. Okay, not just to the first hidden state. In that case, the expressions now become WHX into X, WHH into H, okay, into WH input, okay, IV into V. Okay, these are the features of the images. Okay, we can have the additional term as inputting the features also add corresponding hidden states to take a better caption or a decision. Okay, and this comes as input to the next stage. Okay, and so on. So like this. Okay, so and finally it gives with end. So the like once the sentence is complete, the network itself will be able to predict end. Okay, so this is how the image caption generation is done. So if you understand basic recurrent neural networks and a little bit of convolutional neural networks for feature extraction, you can easily generate captions for a reasonably good number of images. Okay, it may fail also in some cases. Okay, but it reasonably works if the architectures are reasonably designed. Okay, now let us see one of the very important bottleneck or the limitation of this architecture of recurrent neural network. So this is known as vanilla RNN or a simple RNN. Okay, see, if I just pictorially want to depict, I can depict it like this. So input xt and ht-1 are stacked and weight vector is associated. This weight vector means it consists of both weights, WHH, WHX, and it is multiplied and to get the output, okay, with some activation as ht. Okay, you can see this flow here, right? So why this is plotted like this or sketched like this is, see, if I want to connect from time to time, I can easily connect like this. Okay, so you can see here ht, h0 to h1 to h2 and so on. If you see all w's are same here and I'm feeding it them here. Okay, now when back propagation happens, there is one issue here. See, don't bother about this activation functions and so on. See, from h4 to h3, if I just do back propagation, okay, what I will get is W transpose here, one W transpose. Okay, again h3 to h2, if I do back propagation, another W transpose here. h2 to h1, another back propagation, W transpose here. See, now if I want to do back propagation from h4 to h0, how many W transposes will get multiplied in the expression that relates dou h4 by dou h0? Can one of you tell quickly? Leaving out all the rest of the terms, dou h4 by dou h0 will have how many W transpose terms involved? How many W transpose terms involved? Can I get an answer? Quick answer? Yeah. How many? Oh, sorry. Yeah. How many W transpose terms involved? So let us see this. Okay. So here, let us see this. See, if I do this, there will be 4 W transpose terms involved because each dou h t-1 to dou h t, okay, dou h t by dou h t-1 has one W transpose. Similarly, dou h t-1 to dou h t-2, another W transpose, and so on. So I have 4 W transposes. Similarly, dou h10 by dou h1 will have 10 W transposes. So now if I apply some eigenvalue decomposition or singular value decomposition to this weight matrix W, then what will happen? I will get U lambda V transpose. What is this lambda? Lambda is a diagonal matrix of having, okay, some eigenvalues of this matrix W as diagonal elements. Okay, and if I want to find W power 10 in eigenvalue decomposition, if I want to use this help to find W power 10, what I can do is simply U into lambda power 10 into V transpose. Because in eigenvalue decomposition, this is a square matrix anyway, and these two are orthogonal matrices. Okay, so and hence I can easily write like this. Okay, so now lambda power 10. So each of the lambda is raised to 10 times. Now assume that I have a recurrent network and I am applying it over, say, several stages. Say if this lambda is, say, any of the eigenvalues here is lesser than 1, for example, what will happen in that case? Lambda I power 10, 0.1 for example, then this will be 0.1 power 10, that is 10 power minus 10, right? So 10 power minus 1 to 10 power minus 10 it will be. Similarly, if this is 1.1 or 2 power 10 I will get here. So the recurrent neural network architecture that I have just shown has either the problem of diminishing gradients or exploding gradients. In this case, the gradients will explode and whatever you get back propagation, that error will be very high. In this case, error will be very, very low and it don't update the weight matrices. So both are the issues for back propagation. So people suggest different architecture for improving the performance of back propagation or learning of the weight matrices in recurrent neural networks. That is what is referred to as LSTM. Okay, long short-term memory. It has, see, it has a nice provision. What the key provision it has compared to this is they have related the cell state, sorry, they have related the output, say hidden state, to a cell state. And this cell state is only an element operation, though no matrix operations in relating it to the previous cell state. See why the problem has come here? Because each of the HT-1 depends upon HT depends upon HT-1 through a weight matrix. When you have a weight matrix, there are so many eigenvalues involved. Even if one eigenvalue or few eigenvalues diminishes or explodes, there is a severe problem. And this is bound to happen. Greater than 1 or less than 1 is bound to happen while training weight network. But whereas here, okay, I can connect these cell states through a element operation, which is referred to as, okay, F, forget gate. And this F can be, say, even +1 as well sometimes. So that means I don't forget anything. Okay, it can be 0.9, so I slowly forget. Okay, it can be 1 point, it is usually lesser than 1. Okay, so I think I can forget, okay, or need not forget. So I can set it as a, like, even binary value or a small value with sigmoid activation. Okay, something like this. Okay, so this will help me to connect from previous cell state to current cell state without having any matrix multiplications, and easily to like forget or not to forget. Okay, so even if I go for 10 time steps, if I keep all F equal to 1 in somehow, okay, if I manage it to get it reasonably high, then I will not forget. Okay, if it say if it is small, then it means that it is good to forget, as the name indicates. Okay, and every time I will be giving new input as well. Okay, so through input and a gate that tells how much to write, how much to read. Okay, this is the input. It tells how much, what data to read, and gate will tell what to read. Okay, similarly, this output to the hidden state is obtained through output gate. This will tell how much I should write into the current state from the previous state. Okay, where is previous state? In CT. CT is related to CT-1. Okay, and I, G, and F all are related to HT-1. Okay, so this is how the long short-term memory like architecture is designed. So what did it is, see, the previously you had a simple cell, right? So you can see that. So what we discussed here, we have X here, okay, H0 here, or HT-1 here, Y here. So what we discussed is only the hidden state. What is happening in the hidden state? So LSTM also focuses here description of the hidden state. Okay, input and output go exactly like recurrent neural network. Only the LSTM cell replaces the previous hidden cell, okay, or previous hidden RNN cell. Okay, so that is being replaced by this, and with a provision to how much to input or how much what to read, how much to read. Okay, and then what to forget from previous time step and what to output at the given time step. Okay, so they have a nice interpretation and as well as nice ability to back propagate over even long time steps, because the matrices elements here, operations here, are being replaced here with a element operation finally, when you consider in terms of forget gate. Okay, so this is the other way of showing, okay, with the dimensions. Okay, I will skip the discussion here and let's move on. Okay, so now if you see pictorially, what will happen? This is again the same pictorial depiction that we had, HT-1 XT, and this weight matrix consists of all 4 weights. Okay, WH. So you can see this is the whole thing is weight matrix. You can see, okay, 4 times the H is here and 2 times the H is here. Okay, so 4H cross 2H, that is this weight matrix W. Okay, so that is what is here, this. Okay, and through this you can get the how much to forget. Okay, that will give here through element operations, element wise multiplication operations. Okay, so this will enable us to only pinpointedly forget which are the dimensions of the hidden state, some dimensions of the hidden state, and not to forget also. Okay, and this is input and the gate to tell how much to input. Okay, so and then input gate also you can say, and then this is output, how much to write in the subsequent hidden state. Okay, so this way if you see now, even if I connect 10 times, the back propagation happens here through this self state. Okay, easily, even though for HT minus 1 to HT there is a good involvement of W. Okay, so this is how the back propagation in this is somewhat similar to skip connection we have in residual networks. Okay, so you can see in residual networks what will happen, why they are efficient. They can go even up to, say in resonance, they can go up to say 256 layers, 512 layers, 256 layers, and even 1000 layers. The reason is that, okay, the output loss will directly go to the previous layer, to the previous layer, to the previous layer, and up to the even first layers. The some portion of the output loss or the direct portion of the output loss, in fact, will go and it gets modulated to update these input features. So there is a back propagation even in feed forward neural network. When we do back propagation, there is an issue of diminishing gradients that gets nullified greatly through this process of skip connections. So residual connections. Same thing is happening here. This is like a residual connection, okay, or a skip connection, okay, in long short-term memory recurrent neural networks. Okay, so this is the analogy between the RNNs and the recurrent neural networks. I will conclude my discussion here on the theory aspect of RNN, okay, and then move on to the discussion of applications for a very short while. So you can consider it as selective write, read, and so on. As I discussed, this is another pictorial depiction of the same. Okay, so and you can see the same thing. Actually, whatever we have discussed, slightly different here with different notation. So they show that only diagonal matrices or the element-wise multiplications will happen. Okay, in back propagation. Okay, so there is another unit called GRU, like gated recurrent unit, which is a compromise between these two for hardware or say memory less memory operations. Okay, so I will again give a very small pause here. I request for any questions, quick questions before we move on. Yeah, request to tell any quick question, request to ask any quick questions. Otherwise, we will move on to the applications. We will show now different applications. Let me probably complete now because the time is also less. So we can see with this recurrent architecture, there are different like applications that we can target. See, just like I mentioned earlier, so we can generate, say, in many to one output, that is video classification task, or many to many output mission translation task, okay, and so on. I will specifically give a little bit of analogy, okay, or little bit of details of that applications. Okay, so for predicting the next letter, we have discussed in learning. Similarly, the same architecture of many to many can be used for predicting the next word or completing the sentence or the sentence completion. Just we see in our typing, okay, so it will predict the next word. We can also predict the next sentence. Okay, so through RNNs. I will leave here. So the discussion on that. Let's move on. So usually, as any deep learning architectures, data, model, okay, parameters, and the loss function are important here. Okay, so and the for each application, these will vary. Loss function may vary slightly. The features I give may vary. Okay, or the data input and output how I give may vary. The model slightly may vary. While in model, there is usually referred to as encoder-decoder architecture. Encoder means what? See, if I have image captioning problem, I have an image here. I want to encode these features or this information in a compact way. Then I want to decode what the sentence that describes this. Okay, so this can be considered as an encoder and this is considered as a decoder. Okay, So this architecture is referred to a encoder decoder architecture. So in this application of image captioning, encoder is a CNN and decoder is an RNN. Okay, now let's move on. So here as I said, the input can be features can be given to each hidden state rather than single hidden state. Okay, so as I said, this is an encoder and this is a decoder. Okay, so you can write the loss function here can be different. Okay, loss function here I write can be different and so on. Okay, so these are guided by the classification task or the say feature extraction task. Okay, so if I want to do machine translation, okay, so what are encoder and decoder? Or question and answering. Question and answering, what is encoder and decoder? What do you think? Encoder is a say from question, I want to know what the question say it has different words in it. So from each of these words, I want to know what is the features of these words or collective features of these words. Okay, what is the encoding of this English sentence in terms of a vector? Okay, word to vector and then vector to features. Okay, given these features, encoding, embeddings of these features. Okay, embeddings are the features of these words. I want to use them for decoding the answer, right? So it is raining outside, the ground is wet. Okay, so this is the question and this is the answer. So while this itself is an RNN, this is also an RNN. Okay, so this is a application in question and answering is both encoder and decoder are RNNs. Now given say machine translation, what do you think encoder and decoders will be? Machine translation also one language is a sentence, another language is another sentence. So again encoder, decoder are okay, are RNNs. Okay, given say again transliteration is also same. So given image question answering, what do you think is encoder? What is decoder? Encoder is say I have an image. I want to from the image I want to tell and give a question also and answer. See what is the color of the bird? That is my question. I have an image here. Okay, what is the encoder now? I have a CNN encoder to give the feature embeddings or the features. Okay, I have an RNN encoder to understand what is the question. Okay, so I have CRNN as my encoder, both CNN and RNN. Both encodings will be concatenated to decode. Tell that it is white. Okay, color of the word is white. Okay, so here it is many to one, but also you can see that encoder is now both combination of okay CNN and RNN, and decoder is only RNN or simple CNN here because I just want to do a classification white or black or some color only. If I want complex questions answers, okay, then I need a RNN here. Okay, like that. The key in designing all these applications is what is the encoder, what is the decoder that I should use. That you need to figure out. Okay, that is important task for any of these applications. Document summarization. Encoder is RNN, decoder is also an RNN. Okay, so video captioning. So I need to take each of the frames. So these are all CRNNs. Okay, that means CNN extract features, but these features are to be connected to the features of the next frame. Okay, and to the next frame and so on. So each CNN features are to be collected through CNNs. Okay, each frame features are to be connected through or obtained through CNNs, different CNNs. Okay, and then they are to be can have same model, but I think you should extract different features and then you should you should use them through temporal connection as RNN, CRNN this is called as the encoder, and then this is the decoder. You need to give a caption. Okay, so this is also a classification. So CRNN as input and a class like the output is a CNN. Okay, so it's like that. It's conversation machine. So there are different applications that you can target. Say in speech processing, for example. So you need to tell extract features through CNN because speech is a temporal thing. You can connect these features in through LSTM or RNN and can give a better classification. Which is the spoken language here or who is the speaker and so on. Okay, so there are plenty of applications that you can do if you can understand both RNNs and CNNs together. Okay, right, that's all is the discussion I had. So now it's open for questions.
So any questions are there, please raise your questions.
Thank you. Otherwise,
If there are any questions from the audience, yeah. So if there are no questions, let me thank Professor Ramakrishna for a detailed discussion on RNNs, and we felt that as if we are in his classroom, because he wrote and also he demonstrated the calculations. And I hope that this inspires our participants to further explore the field, and we hope that they will learn further in the field. Thank you, Professor Ramakrishna.
yeah, thank you very much. So if anyway, I will share the slides. You can also refer to the video lectures I referred for more details, and you can also talk to me in case if you need any suggestion or
we are sharing the video as well as slides. Thank you.
Thank you very much. Bye. Bye to all.
Thank you. Yeah. So to the participants, now we can take a break, and we'll meet at 11:30 for the next session.